Hi everyone, my name is Toluwani Olorunshola, and today we are going to be breaking down forever chemicals. Just a disclaimer, I'm using earpods because my speaker system for my laptop is bad. What are forever chemicals? Forever chemicals, also known as PFAS, are synthetic chemicals with carbon chains that have their hydrogen atoms replaced partially or fully with fluorine atoms. Why are they called forever, you might ask? Well, they are called forever because of their long-term stability in the environment. They don't degrade. They are used in non-stick cookware like Teflon frying pans, firefighting foams, and food packaging. Because of this unique property, what do you think the unique property is? Well, they have the ability to repel water, food, and oil. And they also resist sticking to substances under high temperatures. Yeah. Unfortunately, with how cool PFAS are, they are linked to cancer, immune suppression, and hormonal disruption, and they contaminate drinking water globally. So, what we're going to cover today is the chemistry behind PFAS persistence, explain how photocatalytic CF bond activation works, discuss other methods to break down PFAS, and discuss implications for environmental remediation. Chemistry of PFAS. The bond strength 485 kJ per mole. That is the strongest single bond in organic chemistry. For reference, the next strongest bonds are double bonds and they start from 700 kJ per mole. Fluorine electronegativity 4.0. This is very strong, the strongest of any element in chemistry. The electronegative nature of fluorine allows it to attract electrons, stabilize those electrons, and that contributes to the strength of the CF bonds, which in turn make the PFAS strong. Perfluorination backbone. Plenty fluorine atoms increase the strength of the carbon. The result is that CF bonds resist thermal degradation, oxidation, photochemical breakdown, and even biological enzymes. But it's important to note that while the CF bond is strong, that alone doesn't explain the hardiness of PFAS. Molecular structure is also as important. Molecular structure. So we're going to be talking about two compounds here, monofluorinated and polyfluorinated compounds. In monofluorinated, there's only one fluorine atom attached to the carbon backbone. And as such, this makes the compound vulnerable to enzymes and more susceptible to oxidation and chemical breakdown. But for the polyfluorinated compound, just like PFOS and PFOA in the diagram, they have many fluorine atoms attached to the carbon backbone. This creates a kind of fluorine shield, like Captain American's shield, that prevents enzymes from penetrating and makes them less susceptible to oxidation. See, the problem now is that humans have produced about 90 million fluorinated compounds in 100 years. But nature had 3.6 billion years of evolution without PFAS. They don't degrade naturally. The solution photocatalytic CF bond activation. Previous approaches relied on traditional metal catalysts. Essentially, you are inserting a metal in between the CF bond to break them. Main group Lewis acid using Lewis as a boron or aluminum based Lewis acid to repolarize the CF bond and make the cutting possible, and harsh conditions like extreme heat, strong reducing agents. The problem with these methods was they were too energy intensive, they released unstable intermediates, and they were very expensive. So the better solution, and we are happy that there was a better solution, is organic photoredox catalysis. It involves four steps: light activation, electron transfer, CF bond reduction, and product formation. In light activation stage, a photocatalyst is oxidized. A photocatalyst is excited by light, and that makes it a good reducing agent. So then in electron transfer, it sends electrons to the CF bond, which now splits the CF bond. In CF bond reduction, it splits it into a highly reactive C radical and F, a fluorine ion. So in product formation, that highly reactive C radical is then combined with hydrogen instead of fluorine. The fluorine is just basically discarded, sent away. Additionally, scientists have also discovered that enzymes break CF bonds. There's particular enzymes that can break CF bonds. Alpha and beta hydrolase enzymes, commonly found in bacteria, they have the ability to remove halogens. Fluoroacetate dehalogenase, they break down naturally occurring fluoroacetate, and this removes fluorine. Enzymes that remove both fluorine atoms from CF2 groups. Enzymes in bacteria like dechloromonas, as you can see in the picture, nostoc, and polyramos suggest that CF bond breaking ability evolved multiple times. The significance of these solutions. Previously, we thought that PFAS were indestructible, that the only option was to capture and store or use methods that required large amounts of energy and give out waste products. But fortunately, they are not forever chemicals. They don't have to exist forever because catalytic methods can break them under mild conditions and with minimal waste produced. And bacterial enzymes like fluoroacetate dehalogenase cleave CF bonds under room temperature and neutral pH, eliminating the need for high heat or high pressure reactors. Current research and future development. What is being developed? Engineered photocatalysts, metal organic frameworks with photocatalytic centers, covalent organic frameworks with built-in catalytic sites, and bioremediation potential. You might ask, oh, what is it? Okay, I'll tell you. Engineering enzymes that can target CF2 groups, combining photochemical and biological approaches. Now, what do you think the problem is? Why these methods have not been implemented, like in real life, like in our everyday today routine? The reason is because of scale. These methods are still being done in the laboratory, and we do need scale to let them progress to treatment plants. Class-based regulation. Now, over 7,000 different types of PFAS are in use currently. The traditional approach to regulate them was to regulate one PFAS at a time, PFOA, then PFOS, for example. This was harmful. The solution is to treat all PFAS as a chemical class, and that makes sense because they have similar environmental behavior and harm risk. How should it happen, you might ask? Well, scientists should use data from well-studied PFAS to estimate risk of others and set limits based on total PFAS exposure, not individual chemicals. The Montreal Protocol Framework for Responsible PFAS Management says that only allow harmful chemicals when they are necessary for health or safety, critical for society, and no safer alternatives exist. Fortunately for us, there are alternatives available for textiles, cosmetic, food packaging, and firefighting foam. Prevention is better than cleanup for PFAS because prevention is less expensive, it stores health impacts before they occur, and it protects water supplies. As you can see, 52 to 84 billion pounds in damage in health costs in Europe. Companies are also using the prevention approach. IKEA removes PFAS from textiles, and Casia Permanente produces PFAS-free products. Takeaways. What we've learned today is that CF bonds are strong but not unbreakable. Photocatalysis offers a path to true degradation, and structure, not just bond strength, determines persistence. Science is advancing. Discovery of enzymes exist that break CF bonds, new photocatalytic systems work under mild conditions, and complete defluorination is achievable. Management requires change. Individual chemical regulation has failed. Class-based approach is necessary, and prevention is cheaper than cleanup. The path forward is to develop photocatalytic technologies for real-world use, implement essential use restrictions, and invest in safer alternatives. These are my references. And closing. So PFAS are called forever chemicals, but science is showing they don't have to be. By understanding the chemistry of CF bonds and developing new photocatalytic methods, we're learning to break down what was once considered indestructible. The challenge now is moving from the laboratory to real-world solutions. But a future where forever no longer means permanent environmental contamination is what we're working towards. Thank you for your attention. Any questions?